Hi, good morning. I'm Jianfeng from Microsoft Research. I'm very glad to have this opportunity to present some of our recent work. I picked a few projects around the topic called agentic modeling. As I show you in the title of the talk, right? This, can you see this? Okay. Agentic modeling by internalization agent harness. So before I go into details, I want to give some definition regarding the three terminologies I used in the title: agentic modeling, internalization, and agent harness. And agentic modeling actually aims to transfer large-scale language models into an autonomous agent capability of performing complex tasks by interacting with the environment. We all know that portraying a large-scale language model is merely a talker. It seems that the model knows everything, but it's really difficult if you ask the model to do something for you. So agentic modeling is the process where we want to turn this talker to a doer. And the so-called agent harness, I think everyone familiar with the terminology. Okay? Usually, because the large language model cannot do a lot of things, it's just a talker. So in order to make the language model to perform some real-world task, you need to couple it with the large language model sort of an agent harness. So when we talk about AI agents, usually it's the combination of the language model, probably multiple language models, and the agent harness. In some sense, harness is a bunch of code. It can handle a lot of things that the current language model cannot handle well. Internalization refers to a process of distilling agentic capabilities from the harness to language model. What are these capabilities? A great example is the memory or context management to use and planning. Typically, this is achieved by mid-training and post-training large language models through supervised learning or reinforced learning. Okay. This figure shows some key components that are needed for agentic modeling. There are three of them. I use different colors. In the left-hand side, this part, it's the agent. For example, we assume that our lab is not building a new large language model because it's so resource intensive. Microsoft has a dedicated team called MAI. They are responsible for building in-house large-scale language models such as MAI. I think they released dozens of models recently. It helps Microsoft stocks. Okay. Again, we have deals, contracts with other companies such as OpenAI. They provide us frontier models. And we have Azure Foundry, which can host hundreds to thousands of open source language models. Yeah. But the focus of the lab actually is to develop enabling technologies to help develop the agent harness. Agent harness can be viewed as hard-coded modules and the layers. They're not models by themselves, but they're modules. Most of them are hard-coded. These layers can do things that the current language model cannot do well. For example, the information layer consists of the memory and the context management, and contains a lot of tools and the skills for the language model to call. And the execution layer consists of a prompt builder, action parser, task decomposition modules, and some error recovering mechanisms. And most importantly, the feedback layer, which helps the system to collect all the trajectories generated by the agents. And these trajectories can be used to refine the underlying model, the LLM, by post-training. This actually is the key of the agentic modeling. Okay, that's the first part. Second part is the environment. And in some sense, the environment, sometimes people call this reinforcement learning environment, or RLEs, okay, where the AI agents can interact with the external world to perform tasks while generating trajectories. And the last component is the yellow one. It's the trainer. It's a model trainer, where the generated trajectories are used to input large language models' agentic capabilities by post-training and mid-training. Some of the, for example, most important training methods are reinforcement learning and its variations, such as on-policy distillation, reverse KL divergence algorithms. Actually, here, for the trainer, the cost efficiency is the key. So it's not only that we require the model to be served in a cost-effective way. More importantly, we hope that the model training is very sample efficient, meaning that probably we don't need a lot of samples to train the model. Putting together, we witness a new paradigm of AI modeling, where harness is like the training data to agentic modeling, just like the internet data to model per training, right? As AI industry and the community are building many AI agents and harness almost every day, then we actually witness an emergence of a new data flywheel, where distillating agentic capabilities from harness leads to AI models that are more capable of doing things, and which these models can help us build even better AI agents that can generate more sophisticated trajectory data and by solving more sophisticated tasks. And again, this process continues as we advance both the harness and the models. Okay? So many of the ongoing AI research projects at the MSR can be grouped into these three categories, as I outlined here. For example, the modeling technology, as shown in the green box, to facilitate harness engineering, such as memory management and test time learning, and the environment service, as shown in the blue box, and to host the parallel many reinforcement learning environments where agents perform tasks and generate trajectories. And actually, this is the source of the training data for agentic modeling. And the yellow box, the trainer. So, in what follows, I will present for each group an ongoing research project we recently released to the public, or we're about to release it. On the environment side, I will present Ultra, which is an open source agentic model framework for research. As for agent harness, I will describe a new test time learning framework called Evolve Lab, which allows large-scale language models to accumulate, reuse, and involve knowledge across a sequence of tasks. And on the model trainer, I will present GFlow-IO, which is a new reinforcement learning method, which I really hope can provide an alternative to the dominating RL methods such as GRP or PPO, because this new method unlock the great diversity and turns out to be a more cost-effective training method. Okay. This is the overall, it's a summary, one slide summary of the Ultra project. And I believe the paper and the code and data will be released sometime next week. We know that despite the rapid progress in AI aging, the open research on agentic modeling remains constrained by infrastructure gaps. Early days when we are doing this pre-training, as long as you have access to internet, there's no lack of training data. You can grab the training data from the web. But agentic modeling is different. You need an environment to run hundreds of thousands of agents simultaneously so that they can generate a lot of trajectory data. And then you can use this trajectory data to train your model. So it's not there yet. In the research community, people have been focusing on infrastructure mainly designed to improve the harness itself, but not the environment that can host different agents to run in parallel. So to narrow the gap, we present Orchard, which is an open source ecosystem for scalable agentic modeling. At the core of the Orchard is a Kubernetes native environment service that provide a reusable primitives of sandbox lifecycle environment. It's called Orchard environment. In some sense, the Orchard environment is like an operating system runtime for AI agents. It acts as an orchestration and a virtualization layer that manages the container images inside the sandbox that expose a clean interface for the AI agents to run. Intuitively speaking, what this does is provide the environment. It's just like the organizer of this workshop, organizer this conference, right? The operating system in this context is like this building, okay? It provides all the electricity facilities to us to host a lot of workshops. If we view each workshop as an agent, then the organizer of this conference did a great job to put each workshop in a particular room. This is like a reinforced learning environment, mini reinforced environment or pod in this context. And after all these workshops, the organizer will, again, collect all the results of this workshop and share the results with us. In some sense, the Orchard environment is the organizer of this the whole conference. Okay? Then in order to demonstrate the effectiveness of this environment, we build 3 agentic modeling recipes on top of that as a demonstration. Okay? First is Orchard environment. First is Orchard Swing. This is target to the software engineering agent. What we did is we distilled about 100,000 trajectories from the models. And then it's interestingly, we see that we got very good results, 73%. If you know this benchmark pretty well, this we bench verified. This result already surpassed a lot of open source models, regardless of the small size of the model. Then we also take 2 other examples. Which is the Orchard GUI. GUI is for navigation. The other is crawl. Crawl is for personal assistant. Now, this is I want to give a quick update of this project. It's test-time learning with involving libraries. Memory is important, but typically we view a memory as a storage of raw experience. But this experience is not learning. This experience, very quickly you will say, oh, I collect a lot of experience previously. I have no idea how to use this experience to solve new tasks. But human learning is different. I never recall all the details of my previous experience. I only remember what matters, right? The failures I try to avoid, the new skills I learned once, and hopefully I can apply it multiple times in the future. So this algorithm is developed to simulate the human learning. Now, the last project I want to give an overview is GFlow IM. The difference between this and the traditional approach, like the GRPO, is that in this reinforcement learning setting, we define policy learning as distribution matching rather than reward maximization. The key difference is that now, using this algorithm, we can sample trajectories, sample solutions proportional to the reward, proportion to the reward they got assigned. Okay. Yeah, I have to stop here. If you have any questions, feel free to reach out to me in an offline manner. Thank you.